we define a trapezoid by 2 points and the projections of those 2 points on the x-axis. Okay, if the points are x1, y1, x2, y2, then the x-coordinate down here is x1, x-coordinate here is x2, and the width of this trapezoid is x2 minus x1. Assuming x2 is bigger than x1, and if it isn't, well, we're doing absolute values anyway. Okay, so, also, what are the other dimensions? Well, how long is this side of the trapezoid, and how long is this side of the trapezoid? Well, the y-coordinate is how far you are above or below the x-axis. So y1 is how far this point is above the x-axis, so the length of this side is y1, and the length of this side is y2. Okay, well now what's the area of this trapezoid? Now there are formulas for the area of the trapezoid. Officially, using geometry, the altitude is the distance between the parallel sides. This would be an altitude, and then you take half of the sum of the bases, and these two would be the bases. Now, on a graph like this, I'm going to use more intuitive terminology. I'm going to say, well, this is a width and this is a height. Okay? I can cut this line segment here at its midpoint with a horizontal line and form a triangle up here. If I take that triangle and turn it upside down and put it here, it fills exactly this region here, leaving us a rectangle. The rectangle still has width x2 minus x1, but its height is what? Well, it's halfway between y1 and y2. Since we cut this thing halfway along this straight line, you can think about that, but it makes a lot of sense. What's halfway between two numbers? How do you get halfway between two numbers? Well, I gave the example. Okay, what's halfway between 8 and 24? What do you spontaneously do? I hope you spontaneously say, okay, add the two numbers, divide by 2, I have the number halfway in between. If you don't, you need to ponder that and get used to thinking that way. Okay, in any case, that makes the altitude of this rectangle, which of course is just constructed by cutting a piece off of your trapezoid and gluing it on to the remainder of the trapezoid, so has the same area. We have a rectangle dimensions x2 minus x1 and y1 plus y2 over 2. Okay, well, the area is then this times this, 1/2 of y1 plus y2 times x2 minus x1. That's 1/2 y1 x2 minus y1 x1 here, plus y2 x2 minus y2 y1. Now, I can express this in terms of determinants. Okay, the y2 x1 minus y1 x2 minus y2 x1 is just the determinant of this matrix. y1 x2 minus y2 x1. Okay. The negative y1 x1 plus y2 x2 is the determinant of this matrix. Negative y1 x1 and y2 x2. So I can express this area in terms of these determinants. I could also have expressed this and started to express it by putting a minus here and switching the columns, but I decided that wasn't going to do a whole lot of good, so I left it the way it is. Now it turns out that both of these expressions occur as both of these 2 by 2 matrices that we're taking determinants of occur as minors of a larger matrix. Okay? And that larger matrix gives you the area of a triangle. Now, I don't want to do all the connections for you, and I want you to have the joy of figuring some of this out yourself. But what do we have here? We have a way of using determinants to get the area of a trapezoid. Okay? Now, if we have a triangle between here, here, and here, and I'll kind of draw this again, just so you see how I constructed it. We actually have 3 trapezoids. Here are 2 of them, right? So we have a trapezoid here that I shaded this way. It has an area. We have a trapezoid here. I'll shade it this way. It has an area. And then we have a trapezoid here that I sketched in yellow and shaded with vertical lines, and it has an area. So if A1 is the area of the part, well, this trapezoid here that was shaded this way, and A2 is the area of the trapezoid that was shaded this way, and A3 is the area of the trapezoid that was shaded with the vertical lines, how could we take those three areas and calculate the area of the triangle? Well, and somebody came up with it, said it's just A1 plus A2 minus A3. Okay, why is that? Well, if I add A1 and A2, I get the area of this whole thing here. A3 is the area of this thing, and if I take this thing away from this whole thing, I'm left with the triangle. So add these two areas and then subtract the area of this lower trapezoid, I get the area of this triangle. Okay? And we also commented, I didn't write this down, and your book discusses it, but you might as well hear it a little bit. What if we did this and got 0? What would that mean? Well, somebody said, well, all the points are on the x-axis. Well, if all the points are on the x-axis, of course, we're going to get all zeros, so we would get 0. But it's not necessary for all points to be in the x-axis. Somebody else said they'd all be in the y-axis. Well, that would be true too, but there's a more general way of expressing the condition, and the condition would be, well, what would you have to do to shrink this triangle down to area 0? Well, I would say if you just keep lowering this point, the area gets less and less until this point approaches the line segment between these 2 points, at which point the triangle kind of disappears. Now, that would happen at the instant this point reaches this line, which would mean that all 3 points are on the same line. Okay? So, in the limiting case, as your triangle gets skinnier and skinnier, its area approaches 0, and you will get a 0 if that point is on the line between the other two, which means all 3 points are on the same line. And we use the word collinear. Now, might be easier if we hyphenate it, co-linear, but it's usually written just as one word, C-O-L-L-I-N-E-R. I spent a month in linear algebra or something course trying to figure out what collinear meant. Okay, so don't feel bad about anything you miss. I never knew what that meant. I knew how to do all the operations on it, but would have been good if somebody had given me a glossary. Okay, so there we have it. Ignore this, it's just pre-calculus. Pretty good pre-calculus. I'd recommend a look at that, but you won't know where to find it. Okay.